If you're preparing for the GAMSAT, today's video is going to be incredibly useful. What it is a recording of a webinar that I recently ran on logarithms. The first half was mainly focused on how you actually do logarithms and the basic skills. So if you've seen my previous video on logarithms, it's basically just a rehash of that. But the second half is all about actually worked solutions of GAMSAT problems with logarithms in them. So I talk a lot about building frameworks to questions, and I think by seeing all these different questions which all involve logarithms, it'll help you see what I mean, and you will see similarities between these questions and differences, and that will help you construct this kind of mental model of what a logarithm question looks like in the GAMSAT. So I hope you enjoy. It is quite lengthy, but it's kind of intended for you to just watch and follow along, try the practice questions. I've got the actual ACER paper at the top of my screen when I'm doing the work solutions, so you will be able to find the actual questions. And I really encourage you to have a go and actually see how you go on these questions, and then you can compare that to my solutions. And as usual, like, comment, and subscribe. If you enjoy this video, please like, comment, and subscribe. And if you want to join any webinars like this in the future, feel free to join my community page. It's completely free to join. I'll leave a link in the description. It's basically just a place where I can upload all my resources. You can talk to me, you can talk to other members, and you will be notified of future events. All right, so logarithms. So when we have a log, it's a function which is like this. And now, sorry if this is a little bit kind of introductory for some of you, but I think it's important just so we're all on the same page. So what this logarithm does is I like to think of it as a question. So basically, this question is saying, and I'll try color code this, how many times do I need to multiply the base, sorry, just letting someone else in, by itself to get the number. So this is the number in the brackets. So basically, if you look at the color coding that I've done, this is saying that to get 1000, we need to multiply 10 by itself 3 times. And that kind of makes sense, doesn't it? Because if we multiply 10 by 10 by 10, that gives us 1000. Now, something that is kind of related to this is actually if we had something in the form of an exponent. So what this does, instead of being a question, it's more a statement. So it tells us how many times to multiply the orange base by itself. Maybe if I put in 1000 here as well, because that's what that equals, to get the number. So you can see that one of these is a question and one of these is a statement, but the exponent form, so the statement over here, is almost answering the question on the left. So what I'm trying to allude to is if we make the number into this form, then that actually just answers the question that the logarithm's doing anyway. So I'll show you what that means. So it's good to just kind of understand what's going on, but logarithms can actually be quite simple to solve. So if you have log 10 of 1000, now I know this equals 3, but what you can actually do is just convert that 1000 into scientific notation. So that would just become 10 to the 3. And the answer is just that number over here. So really it's a two-step process. You just convert the number to scientific notation and then you just take the exponent. And the reason that works is because when it's in that form, when it's in the scientific notation form, the exponent really is the answer to the question that the logarithm's asking anyway. So we're kind of just going in a full loop. So I hope that makes sense, but really it's a two-step process here, and it works for any logarithm. So if you had, any number. So if you had a small number like that, we just go 1, 2, 3, 4, and then this would be -4, because that would be 10 to the -4. So this number just becomes the answer. So really just convert to scientific notation, and then the number, the exponent of the number in the brackets will just be your answer. So that's all pretty straightforward, but the first little quiz question that I want to give to you guys here is, what if we had something like log 10 of 3,000? Does anyone want to be brave and hazard a guess to what that would equal? Between 2 and 3, or 3 and 4? Yep, that's good. Why do you say between 3 and 4, Marie? How did you get to that conclusion? Is anyone thinking 9? Because we kind of end up with this 3 by 10 to the 3. So if you're following my process, there's this 3, that just comes over. But then what about this 3? Does that multiply by that 3? So really the whole point of this was to just show you there's a common mistake that I see with these logs. So some people say that this equals 9. But if we had log 10 of 10 to the 9, which is like a billion or something like that, that would also equal 9. So we know it's not 9, and Marie's perfectly on the money in terms of how a log scale works. So if we look at 3,000, the log 10 of 1,000, as we just did before, would equal 3. And then log 10 of 10,000 would equal 4. So this number, being somewhere in the middle of these two, is somewhere in between 3 and 4. So that, in my mind, is the level of detail that you need to go into for the GAMSAT. And if you said something like 3.5 or 3 or 4, you would probably get the right answer. Anyway, so it's not really too important, but I just think it's really important that you don't fall into that trap. And you just know that this 3,000 is somewhere above 3 and below 4. And just to kind of go with a more concrete process, what I do is, because the only numbers with logarithms, at least with a base 10, that are going to have a clean number, like a full round number, are going to be factors of 10. So things like 10, 100, 1,000. So if I ever get something like log 10 of 3,000, and it's not, I know that's not going to be a whole number, what I like to do is just round this number to the nearest factor of 10. So the nearest factor of 10 to 3,000 is 1,000. And then I would convert that to 10 to the 3, and then that would be my answer, would just be 3. So it's an approximation, but approximations are generally fine in the GAMSAT. And I find this is good because if you had something like 8,000, you're going to round it up to 10,000 and then get a different answer. So I think that's just a nice little way to handle a log if you have all these different, these not clean numbers, if you will. That's kind of how we solve logs, but there's also situations where we might have a logarithm and it actually has a variable in the log. So something like x. And sorry if my screen's a little bit laggy. It's just it's the best I can do. It's a low budget setup that I've got. So we've got log 10 of x, and that would equal some number. So let's say 5. So just conceptually, if you think through this, does anyone know what x would equal in this sense? So I'll zoom out a little bit. So maybe I'll write it back up here so you can see the question. So try to, I find this question, if you can remember the question of what the logarithm's saying, I find this is really, really helpful to fall back on, just to get through. So does anyone know what x would equal? 100,000. Perfect. Yes. So it would equal, you actually did perfect. So I jumped a step there because I was just going to say 10 to the 5. So this tells us how many times we need to multiply 10 by itself. So x would just equal 10 to the 5, which then equals 100,000. So that's really good. Now, it's good to have that conceptual understanding, but also we want to do it quickly. So the process that I say is I move the 10, so the base of the logarithm, and this is going to be important for natural logs as well, because they have a different base. So at the moment, we're just doing the base 10, but just be aware that there are other bases. So this is only for base 10 at the moment. So just try to remember this when we get to natural logs. So what I say is I move the base of the log down and just make that a nice big number. And what I do is I then write the whole logarithm, so this whole side, as the exponent of that base. So this will just take a little bit of getting used to. But what actually happens here is when that is the exponent of the same base, these actually cancel out, and what you're left with is just x. Now, to make any mathematical thing work, we need to have the same thing on both sides of the equation. So we need to then bring that same base down here and make the thing on that side also the exponent. So that becomes 10 to the 5, which is how we got that. So when you practice, it's good to just practice a few of these logs and just get comfortable with kind of making the base. I don't really know what the mathematical term for this is, but making the base the big number down there and then putting the log as the exponent to that base. I feel like that doesn't make sense when it comes out of my head, but hopefully, at least graphically, that all makes sense. The other thing that I'd like to kind of just briefly go through, so the log 10 and the 10 cancel out if the log is the exponent, but we can also use a log to kind of cancel that out. So if we had 10 to the x equals, let's say 100 or something like that, you can get rid of this 10. So how you would isolate the x in this case is taking the log of that number. So log 10 of that will then cancel it exactly the same as how we did it there. We'll cancel out that and the 10. So then x will just equal, because we need to do it to both sides, x will equal the log 10 of 100. So that will equal 2. Okay, so and that kind of makes sense if we go back to our original thing. 10 to the power of 2 equals 100. So just to prove to you that this is not any mathematical hocus pocus, it is actually it does actually work. So you'll get more and more comfortable with using these things to isolate the variables that you need. A few useful index laws that can be helpful with logs. So if we ever have 1 over a to the m, this will equal a to the negative m. Okay, so very often you actually, so a lot of people can do things like log 10 of 100, for example. We've kind of gone through a pretty rigorous process of how to go through that. But where people do struggle sometimes is log 10 of 1 over 100. And you can kind of go through this process, but if you can kind of go through it in scientific notation and get to an answer anyway. But it's just this is quite a handy thing to remember. So if you make this log 10 of 1 over 10 to the 2, then you can just make that 10 to the negative 2. Okay, equal. And just to prove that to you, this number, 1 divided by 100, would be 0.01, and then that would be 1 times 10 to the negative 2. So just to prove it to you that these are the same number, but that's just a good little one to remember. And the reason I say that is very often you get into this situation, but it's also the other, where it also becomes helpful is with this log law. So if you have any number, if you have two products for that exponent, you can actually, this is the same as m times log an. Okay, so that's a little bit confusing, but basically what's happened here is I'm just saying that these two equations are exactly the same. And what that means is if you can separate, so let's say you had something like 10 to the 20 or something like that, you can break that into 10 to the power of 5 times 4, okay? And if you can break that into its products, you can take one of those values out the front of the log and not change its value. And why I'm telling you this log law is, well, just keep it as a hint, because there's a question coming up where I think this might be useful. But when you have this negative power here, you can then take that out the front of the log, because it's the same as -1 times 2. So it means we can take the negative out the front of the log. So just to go through that here, if we had log 10 of 10 to the -2, this would be the same as negative log 10 to the 2. Okay, so if you get stuck, what I want you to remember is if you get stuck with some kind of number with 1 over a number, make it into a negative power. And if that negative power is still tripping you up, you can take the negative out at the front of the log. Okay, so that's all. That's just a little, kind of like a little breadcrumb for what might be coming up later. So that's everything on log with the base 10. As I was talking about before, you can also have these things called natural logarithms. And what they are is log to the base e, where e is 2.7 something or other. Okay, it's like a big long recurring number. That's Euler's number. So what this is saying, if we go back to our question really quickly, how many times do I need to multiply 2.75 whatever by itself to get the number? So you can see already what the problem is here is that because it's such an irrational number, it's very hard to actually work these things out. So usually in the GAMSAT, they're going to give you the value. So they might say natural log of 10. You can't work that out without a calculator, so they have to give you this value, okay? So generally solving natural logs is quite easy because they give you the number, but yeah, just be careful of a few little traps. So I might not say it because I'll see. I think it's better if you see it in the questions, but there might be some traps associated with the numbers that they give you as well. So that's kind of solving logs done. And then we also have rearranging logs. So if you had natural log of x equals 4, can anyone tell me what that would equal? So just follow the exact same thing. If you can remember, we had our log and then we brought the base down. So what's the base? We dropped the base. Perfect. E to the 4. Beautiful. So this is basically log e. So we bring that base all the way down, e to the power of natural log of x equals e to the 4. And then e and natural log just cancel out. So x equals e to the 4. Now, if you had to approximate this, I don't think you will need to, but you can always just round that to 3. So you could just say this is the same as 3 to the power of 4. So maybe you would get an answer where you might need to approximate 3 to the power of 2 or something like that. Maybe. So just good to keep in mind, if you see e, you can just basically replace it with 3. 3 and e. That's nice. And last thing is just if you have e to the power of x equals 3, then you can just take the natural log to cancel that out. So you can just use natural log of that. They will cancel out, and then x just equals natural log of 3. Okay, so all the same principles apply. If you have a really good understanding of logs with the base 10, you shouldn't really have any problems with natural logs. So we're going to start with this one. And I might just give you a couple of minutes just to work through it and see if you can come to an answer yourself. So I know it's a little bit small. I can probably zoom in a little bit. Hopefully that's big enough to see all the words. It looks okay to me. So I'll give you guys a couple of minutes just to try to work through this one yourself and see if you can come to an answer. Maybe while those who are working through it, I might just go through at least how I think about starting a question like this for those of you who are a bit stuck. So I think when I think of GAMSAT problems, I really think of two parts of it. So the first part is really the problem solving part itself, where you have to kind of interpret what the question means, maybe, interpret what some variables mean, stuff like that. And then once you've solved that, it's usually the application of a skill. So what we've kind of done in the first part is just learning that skill. So that skill's quite isolated. And I guess if you're really good at those skills, you can think about what am I missing to use that skill? So if you get more confident in the skills, you generally look for ways that you can use that. So obviously we're going to use a log because we've got this equation. So I would just be thinking, what am I missing? Like, what do I need and what am I missing? So I really like summarizing questions into 2 or 3 words. I think I went through this in my last webinar, actually, the 3 words rule, but I think it's really quite good. So this one's actually a little bit hard for 3 words. Maybe I would go with comparing. I'm going to use 4 words. Sorry. Breaking my own rule. Intensity level and intensity. God, I can't write. Okay, so they're my 4 words. So I think it's just good to think about when you can summarize it into these words, when have you done something similar? Okay, so if we're comparing intensity level and intensity, when is the time that you've compared 2 things? Now, this could be anything in life or in the GAMSAT or anything really, but I think if I'm comparing things, I really want to work out what one equals and then compare it to the other. Sounds pretty self-explanatory, but that should hopefully help you kind of, this is actually quite a bad example. You kind of need more than 3 words, but the key thing that I want to capture here is that comparing. Okay, so comparing is the key word about how you actually solve this problem, is you need to compare 2 situations. Now, what are those 2 situations? The threshold of pain and normal conversation. So it's very important to be quite specific when you're doing these questions as well, because you can already see what they're doing. So they've got sound intensity level, sound intensity. So they're purposely using these words that are very, very similar to each other to try to get you confused about what refers to what. So when we look at this table, this is sound intensity level. So it seems like it's the same thing, but it's not the same. So if we look at normal conversation and threshold of pain, a lot of people, so the first trap that they're trying to get you to fall into is that this is 2. Okay, obviously not. Don't do that. If it's an easy thing like that, it's probably not the answer. But what we have is sound intensity level. So now we need to understand how we can actually calculate sound, how we can relate sound intensity level to sound intensity, and that's where our equation comes in. So we've got sound intensity level, which is LP, and sound intensity, which is I. Okay, so we actually need to find I in 2 different conditions, don't we? Does that make sense to everyone?
Yeah.
It's a little bit clumsy how I went through it, but I hope that kind of helps. So I think it's just good to simplify things as much as possible, but be very specific with what you're actually trying to work out. So we now have 2 sound intensity levels, so we can apply this equation. So 60, so I'll just do normal conversation because again, I'm comparing things. 60 equals 10 log. If it ever says log and it doesn't give you a base, it's base 10 unless it's a natural log. I over 10 to the negative 12. Okay, so now if there's any number at the front of a log, I just like to get rid of it. So I just divide this by 10. So I get 6 equals log 10 of I over 10 to the negative 12. So broadly speaking, I would put this in the realm of rearranging a log, because I have a variable within the log. So even though there's that 10 to the negative 12 in there, don't worry about that yet. You need to rearrange to get rid of this log so you can keep going. So how we get rid of the log is make the base down here equals 10 to the 6. They cancel. So we get 10 to the 6 equals I over 10 to the negative 12. Then we can times that by 10 to the negative 12. So I equals 10 to the 6 times 10 to the negative 12, which will then, if we just apply our log laws, will just equal 10 to the negative 6. All right. So that's what I equals with the normal conversation. Now, really, once you've done it once, it's very easy to do it a second time because everything's staying the same except one number. So instead of 60, this will just be 120, right? So let's just carry that through. So if it's 120, this will be 12, this will be 12, this will be 12, this will be 12. So this will equal 10 to the 0 or 1. So if we compare these numbers, this is an increase in sound intensity of 10 to the 6. Okay, just by comparing those numbers, that's times 10 to the 6 to get there. Anyone else still having trouble? What about Ola?
I just have a question.
Yeah.
Right at the start where you just did to get rid of that 10, you did divide it by 10. Is that do that with any number that's in front of a log?
I think generally it'll work. I think you can't really work with a log if there's something at the front. It's kind of like if you've got, x plus 2 divided by 3. I'll write that out. You can't really deal with that plus 2. At least you probably can if you're really good at maths, but I think just keep it simple. You're going to need to deal with that 10 anyway, so just divide it out. So any number at the front of the log, I just get rid of it straight away. And kind of like here, you can probably work out, there's probably some fancy mathematical way to do it. I would just multiply by 3 every time to get rid of the 3, and then I can work on the 2. So I just do simple maths well, and I think my simple brain just says divide any number out the front of the log, just divide it to the other side. Next one is this one. So you can see that we've kind of gone from physics into chemistry, but I promise that this is still logarithms. All right, so I'll give you guys a couple of minutes again just for this one. So maybe we'll try workshop it a bit. What's the first problem with this? So there's some variables we don't know. I guess really we don't know what pKa is. We don't know what this is. We don't know what that is. So I would be trying to think, how do I define what these are, and try to define them in the most simple terms possible, because really it's about coming up with nice, easy explanations for quite complicated information. So if you can explain this really simply, then that will be good. So does anyone know what the pKa is? 6.37. Yeah, exactly. So really, this is probably a good example of how you can skim through the text. So just skimming through the first 2 paragraphs, I don't see anything about pKa, so I wouldn't even look at it. But down here, I find pKa, and I'm like, okay, well, I've got 2 values of pKa. This is like my first hurdle. Which one do I pick? Do I pick this or this? Well, it refers to this and this. And then I see, oh, well, that's the same one. Seems pretty reasonable to use 6.37, doesn't it? So we've cleared our first hurdle. pH equals 6.37 log A over HA. So what is A? What is A and what's HA?
Are they both 0.150 moles?
Yeah,
Uh,
perfect. Yeah, no,
all
you
right.
kind of jumped the gun a little. But yeah, that's exactly right. So these are the values that you'd put in there because HA is the weak acid and A is the conjugate base. But in this case, the concentration of them is the same. So, or at least it's reasonable to assume that because we need the concentration, but yeah, I mean it's the same volume of each one, right? So we end up getting. I'll just rub this out. So yeah, just define the terms and then put the numbers in. So 0.150. So what's that going to simplify to?
1.
1, exactly. Paris, I wouldn't remember what the common acids and bases are. I don't think it's. I mean, would you think that it's? I don't think it's particularly helpful for this question. So until you find a question where it would be helpful to memorize a common acid or a common base, I'd probably not do that. And I haven't really encountered any questions where, I mean, if anything, you're probably asking the wrong person as well, because I'm very much on the side of don't memorize much at all. I think you can work out a lot based on the information you're given, and that's what I would focus on. Some other people may feel differently about memorizing things, but I'm probably too far the other way of like don't memorize anything. Okay, so going back to this process. So we've got a number, we need to solve it. What's our two-step process? First step is convert it to scientific notation. What is 1 in scientific notation? It's actually a little bit tricky.
1 to the O?
It's, well, that's correct. But remember, we need the number at the base to be the same as the logarithm or else it doesn't work.
1 times 10 to the minus 1 times 10 to the 0.
1 times 10 to the 0, yeah. So it's 1 times 10 to the 0. So any number to the 0 equals 1. So we can just make this 10 to the 0. And then the second step of our process is just that becomes the answer. So this simplifies to 6.37 plus 0, which is just 6.37. So therefore our answer will be equal to the pKa of dihydrogen carbonate, because that's where we got that pKa value. Now, if we look at this next one, what's another good thing is, well, we just did that. Like we just did that process. Why can we not do that again? Or can we just do that same thing again? So what we did in this case was we put the two values, the two concentrations, just straight into the formula. So can we do that in this case? What do you think? Yes or no? What's your gut feeling?
No.
Yeah, no, because there's different volumes, isn't there? There's 40 mils and 25 mils. So in this case, we need to kind of standardize that. So concentration equals ice cream or N over V. Good one to remember. So I know I just said don't remember anything. I'll backpedal a little bit, Paris. Remembering some formulas is very handy. So N over V, we have concentration and volume. So I would just rearrange this for N. So I'd just say N equals CV, and then we can just plug our numbers in. And I'm going to be a little bit loose with the numbers because they're both in mils. I know you need liters, but I'm just going to use mils just to get, because all I really care about is the ratio of one to the other. So I don't actually really care about exactly how many moles there are. I just want to know how big one is compared to the other. So as long as I'm using the same units, that'll be fine. So this would just be 2.5 by 10 to the negative 1 times 40. So 2.5, I'm just going to make it, yeah, times 4. So then these will cancel out. I'm being really loose with the the maths here, but it's more about the logarithms anyway. So this equals 10. So I guess what I'm trying to get across here is I'm doing really bad maths, but if I'm consistent, I will get the same incorrect answer for the other thing, as long as I do the same thing. So if I do the same thing badly, I probably should have just done it properly rather than teach you guys bad habits. But I'm just going to be consistent here. So I'll say 2 times 10 to the minus 1 times 25. So this is going to be 2 times 10 to the minus 1 times 2.5 by 10 to the 1. So this will just equal 5. So you kind of see what I've done there. So the numbers are all whack, but the main thing is, because we're putting them into this fraction, we only care about how much of one we have to the other. So kind of, do as I say, not as I do. But we can see that we actually have double. Does everyone agree that we have double of this one? The one that I did first, which refers to here, we have double of that.
Mm-hmm.
Everyone on board? So which one? So that means in this formula, we have double of one compared to the other. So which one? I'll zoom out a little bit so we can see everything. Which way are we doing it? Are we doing it 10 over 5 or are we doing it 5 over 10? Which one goes on top? Which one goes on bottom?
5 over 10.
So if I'm comparing these two, I don't, to kind of go back to what Paris was saying, I don't really know which one is the base out of these two because I've never heard of them. And that's kind of the point, is that you're not meant to have heard of them. So, but if I compare these, the PO4 is the same, the PO4 is the same. This one has one extra hydrogen, plus one hydrogen, and this has one extra sodium. And I kind of associate sodium with being basic and hydrogen with acid. So I would say that this is the acid. Now, just another little trap here. A lot of people would think that A means acid. Very easy mistake to make under time pressure. So it's just very important that you clarify everything. Same as the last question, be very specific with what you're doing. So that's not the acid, that's actually the base. So as Ollie said, it's 5 over 10. So our pKa, just to jump forward, is just 7.21 because we're using PO4. So our pH will equal 7.21 plus log 5 over 10. Does anyone want to have a go at solving that? So they've given us a value here, log 10 of 2.
Well, you can simplify to log half.
Yep. So if we have log 1/2,
And then, that will be the inverse
perfect.
of log 2.
So it'll be log 2 to the negative 1. And then we can just, so this is what I was talking about before, we can bring that 1 out the front. So negative 1 times log of 2. So we end up getting 7.21 plus minus 1. I'm going to just do it all out and then we can simplify it later. Plus minus 1 times log 2, which we have the value for, which is 0.3. 0.3. So these will become a minus. So 7.2 minus 1 times 0.3. So 6.91. God, what is wrong with my writing? 6.91. Okay. Now, I think just a good thing to think of is if they're giving you values, ACE is smart enough to know that when people have no other option and they're guessing, they're going to assume that you need this value because why else would they give it to you? So I think why they do, you often end up in the situation where they've given us log 10 of 2, but you end up, as we found out, log 10 of 1 over 2. So I think they do this so because people can probably piece together that you use this 7.21 as the pKa value, and then they'll just assume, because they don't know, I'm just going to plus 0.3 in there. So I'll get 7.51. Okay, and of course that's an answer. So I think it's really good to look at the traps that ACER puts in there, because then you'll be more aware of them next time. So using things like A actually being the conjugate base, giving you a value, but then you actually need to use the inverse of that value. These are all really common things, and it's just good to kind of almost like psychoanalyze the person who made these questions, because then that gives you a bit of insight into what traps there's going to be. Okay, and we'll just go through this one quickly. So in this case, it's essentially exactly the same. So that's why I'll go through it quickly. So they've told us here that the pH is 7.4, and we need the amount of dihydrogen carbonate in comparison to sodium hydrogen carbonate. So this would just be 7.4 equals, now we know that the pKa of hydrogen carbonate is 6.37. So I'm just going to say 6.4 because that makes it nice. Sorry, not equals. Plus A over HA. So if I just, so it's log. So if I just minus 6.4, that will cancel that out. So we get 1 equals the log 10 of A over HA. Then to get rid of the log, we just do the dropping the base of it. So 10 to the 1 equals A over HA. And then from that, you just need to determine how much of the acid you have in comparison to the base. So I just wanted to go through that one quickly because it's essentially the same process as what we've been doing. So I don't think there's too much value there, but I just wanted to show you to get a bit more of an appreciation about how these questions could kind of present themselves. They're kind of either going to give you, either give you this thing and you need to work that thing out, or they're going to give you this thing and you need to work that thing out. But it's basically the same skill. So once you've got that and you're kind of aware of how to do it in one setting, you can kind of do it in the other. Now we're going to finish with a hard question, but before we do that, I just want to also show you this question because this is also kind of assessing logarithms as well. So we'll skip 104, but have a look at 105. So we'll go through this one just quickly again. So I think it's just good to show you some of the traps that are there with logarithms. So best estimate of the reduction of the normal bacterial population between drenching and day 7. So the normal, which one's the normal one? What am I doing? So I think it's this one, line 2. Yeah, the upper line. Okay, so we're looking at this line and we're looking between drenching and day 7, which is here. So we're looking for this decrease. Now, so if you look at this, you might say, well, it's gone from 10 to the 8 to 10 to the 6. So the answer is 10 to the 2. But this isn't quite how logarithm is. I know this is powers, but it's very similar to logarithms. And you might see log scales like this. So if you actually think about it, 10 to the 8 is, so 1 times 10 to the 8 is 1, 1, 2, 3, 4, 5, 6, 7, 8. Huge number. 100 million. And 10 to the 6 is actually 1 million. So our decrease is actually 99 million. Just in that. How do we know it's a log scale? I think, so it'll either say like log 10 to the 6 or something, but I guess what I mean by a log scale is more an exponential scale. So if you see things like this, like you got 10 to the 5, 10 to the 6, 10 to the 7, it's not saying, it's not a linear scale. Linear would be 1, 2, 3. This is going up in powers of 10. So, oops. So yeah, it's a bit of a trick here. And another one I've kind of seen in the same vein is which one decreases more? Maybe we take it at this point. So line 1 or line 2 between these 2 points. So which one goes down more? Line 1 or line 2? I've made this way messier than I needed to, but we carry on. So your brain kind of automatically thinks, well, it should be line 1 goes down more, right? Because it's a steeper decrease, but it's not, because again, here, this value corresponds to 100 million, and this value here, let's just call it 10 to the 7, just for argument's sake. That's 10 million. So just going down that small bit, even though it's flatter, is a decrease of 90 million. Whereas going from here to here, we've gone from, let's say, 10 to the 6. Let's even be generous. We'll say that this equals 10 to the 7 as well. We've gone from 10 million down to, let's even be more generous, and we'll say it goes down to 0. We've still only decreased 10 million. We haven't gone down anywhere near 90 million. So just be very, very careful when you get any kind of exponential scale like this, that you're really double checking your answers. Because if this was a linear scale, again, if this was 1, 2, 3, 4, 5, 6, 7, then of course it's the red line. But exponential scales are completely different. So really good to be aware of that. Just have your alarm bells going off anytime you see something like this on the graph, okay? Last one. So there's a few things. I thought I'd just throw a bit of a hard one in there that isn't about calculating logarithms. It's more about rearranging logarithms. So here we need 2 things we need to understand is that any time we see a p, it means negative log 10. Okay, so we can substitute a p for a negative log 10. So when we have ph, it actually equals the negative log 10 of whatever's to the right of that p, which is, in this case, hydrogen ions. Okay, so if you had POH, you guessed it, negative log 10 of OH. All right, so that's what the p means. So anytime you see a p, it just means negative log, and we can kind of substitute those in for each other. Now, the last thing is there is one log law. This is why I wanted to go through this question, because I didn't cover it in the kind of workshop-y thing at the start, because it's a little bit out of context. So we have this log law where if you have 2 products in here, so again, if we can split that number into 2 products, this will equal log A plus log B. All right, so let's just say we had something like log 10 of 100. As we should know by now, this equals 2. But if we split this, we could split this into log 10 times 10. And then that would equal log 10 plus log 10. And log 10 just equals 1. So this just becomes 1 plus 1. Oh, 1 plus 1, which equals 2. So we've got the same answer. Okay, so that's just a good log law to know, especially for this one, is if you can break something up into its parts, then you can if you can get products of a number, you can then split it into 2 separate logarithms, and that can be helpful sometimes. I might just leave that there. So I just want to give you the answer for 109, which is A. Okay, so really what I want to focus on is this one here, because we want PKB. Okay, so we work out KB. I think that one's really just rearranging a formula. I'll show you quickly how I got that. So we need, what I'm looking at is I obviously need KB. So I've got this formula here, which looks good. But again, what's the hurdle? What's the thing that I need to jump? I've got the wrong variables. I need some of these things in there. So I think back and I think, how have I introduced new variables before? Well, I substitute other equations in. So I see this one, which has KW and H3O, which is exactly what I need. So I would just say that this one equals OH. So if I just divide both sides by H3O, I get OH equals KW over H3O. And then I can just substitute this one back in there. So KB equals BH times KW over H3O B. I've done a bit of a weird order, but that's A. All right, so I just want to rush through that, but basically that's how you solve the first one, is just substituting formulas. So with that knowledge, we have KW BH over H3O B. Now we need to find PKB. So I'll start you off a little bit. So P, remember, is negative log 10. So negative log 10 of KB will, so if we negative log both sides, sorry, that's what I should have said that. So I negative log both sides. Is everyone with me so far? I feel like that was a little bit confusing, but I did that. I negative logged everything so that we now, I'll rub that out. We now can substitute that. That can be substituted for PKB, right? Because negative log just equals P. So anytime you see a negative log, you can just substitute it for P. So I'll let you guys, so that's the starting point. Now we obviously need to start breaking this log up into its individual parts, and we need pH and stuff like that. So I'll leave it here for a couple of minutes and see how you guys go. And I'll bring this log law down. Maybe I'll do both, so we can see everything that we need. If this is difficult, again, it's meant to be difficult. So you can watch this video back a few times. You'll now have the solution as well. And I guess what I want you to do is think about what you can take away from that for the next question that you're focusing on logarithms. So don't worry too much about this solution, but definitely watch this a few times to see how I'm thinking about it, how I'm working through it, because you don't need to follow everything that I'm doing to a T. I guess what I'm trying to do here is just show you different ways that you can think through these problems and different little techniques that you can use. So, you'll have this recording. You can watch those solutions, see how I think, and then what I want you to take away is, don't try to memorize that solution. Think about what you couldn't do and therefore what you need to study a bit so that you can do that if you needed to on the GAMSAT, because these are all kind of the skills that you need. All right, everyone's stuck. So that's all right. So let's just work through this. So again, let's identify our hurdles. Okay, so we've got something that looks a little bit, something that doesn't look that bad. It's kind of similar-ish, but our problem is that we've got this log with all of the things that we need in it, and we kind of need to separate that out. Now, remember what I said, P equals negative log. So when I'm seeing these things, I'm thinking this could be the same as negative log KW or negative log, it says it up here, so PH, H3O. Okay, so I'm thinking of ways that I'm thinking, how do I get from what I've got to one of these things? Well, I have KW, so I just need to negative log it. I have H3O, I just need to negative log it. And I actually have BH and B, they're already in the log, so I actually don't need to do anything with them. If I can take these out, that's kind of the first thing that I'm trying to solve in this problem. So what I would do is I would break this up. So I don't know if this is a necessary step, but I'm just going to move this negative to the other side. So just pretend that I'm dividing by -1 on both sides, which means I'll get a negative PKB. So I'm just doing that because, again, I'm not that confident in my ability to operate with those negatives. And to me, it just seems simpler to move the negative to the other side, and I can always bring it back later. So I've got this. So I'm going to rewrite this as log 10 of KW over H. How am I going to? I'll do this. Yeah. I'll do this first, times BH over B. So as I said, the first hurdle that I had was getting those things out, but I can actually just leave those other ones in there because they stay in there. So using this log law, we can just end up doing these ones together and these ones together as separate logs. We can just split that log. So we get log 10 KW over H3O plus log 10 of BH over B. Perfect. So that bit's kind of done. I know that's there now. I need to work on this. So how could I do that? Well, I know that I can separate that if I have them as two separate products. So what I might do, so again, it's just about what do I want? What's my optimal configuration of these numbers? So log 10 of KW over 1 times 1 over H3O. So you see that if I multiplied these numbers together, they would give me that, wouldn't they? Because I can divide anything by 1. Like that's kind of, I've just separated this as two individual fractions, but that does equal the same thing, doesn't it? Plus log 10 of BH over B. So you see, it's a really just step-by-step process. What's my problem? How do I solve it? Because now, once I've got these as separate products, I can apply my log rule again, and I can separate them. So now I get log 10 of KW, because KW is just over 1. I might actually move down to the bottom here, because I'm running out of space. It's a very messy question. So I'm separating this because I've got two products, log 10 of KW plus log 10 of 1 over H3O plus log 10 of BH over B. Now, what am I going to do with this one? 1 over.
To the -1.
Perfect, exactly. So log 10 of KW plus log 10 of H3O to the -1 plus log 10 of BH over B. And then, as I said, I can just take that number out the front, can't I? So that's just going to make this turn to a negative. So I get log 10 of, I know I'm just rewriting the same thing, but to me, it's the easiest way to do it, minus log 10 of H3O plus log 10 of BH over B. Now, I'm just going to, this looks really frightening actually, but I hope you could see it. It's quite a lengthy mathematical equation, but it's not actually that difficult. I'm just doing really simple things. So I actually notice now negative log 10. What have I been talking about? Negative log 10 P. That actually does just equal pH. So if maybe I'll go up here. now. So this is, so remember, this is all negative PKB equals this. So negative PKB, I'm getting all the way from the start here. I've just left it out because I'm writing too much. Equals log 10 of KW. Negative log, this is just going to become plus pH. Yeah? Plus log 10 of BH over B. Now, everything's looking really good, and I'm thinking I'm really close to an answer now. So now I'm going to bring this negative back over. So PKB, so I'm just going to divide everything by -1. So when you're dividing a number by fractions that are added together, that's all right, Paris. Pretty much at the end now anyway. Thanks for coming. So when you're plussing these fractions, if I divide this by -1, I actually need to divide all these terms by -1. Okay, so that's how, if you're adding things, you need to do it to all of the terms. So PKB now becomes negative log 10 of KW minus pH minus log 10 of BH over B. And then again, I'm spotting that pattern of negative log 10 becoming a P. Christ, this is, so that's going to become PKW minus pH minus log 10 of BH over B. So we got there, which is answer B. Does everyone see that? So PKW, I'm going to run out of colors, minus pH minus log 10 over B, H over W, B. And that's the end. So if you've made it this far, well done. But I think if you can follow along with everything, it gives you a really good basis for all kind of logarithm questions in the GAMSAT. So I hope you enjoyed. If you did, please like, comment, and subscribe, and I'll see you in the next video.